Okay, let's unpack this. You know how in the tech world, especially with these huge AI models, it feels like you always have to trade off speed for volume.
Yeah, it's like a constant push and pull. Low latency, so really fast responses,
Right.
or high throughput, handling tons of requests. Usually you can't max out both.
Exactly, like pouring water, right? One glass fast or lots of glasses slow. It's that classic trade-off we see everywhere.
It really is a fundamental challenge, trying to get responsiveness without sacrificing the overall workload capacity.
Which is why this recent article, Lower Latency and Higher Throughput with Multi-Node DeepSeek Deployment, really caught my eye.
The title alone kind of makes you stop and think.
Totally. They're saying with their model, DeepSeek V3R1, it uses that mixture of experts, or MoE, approach.
Uh,
They can actually get both faster speeds and handle more stuff at once just by using more computers, more GPUs in a multi-node setup.
it flies right in the face of that conventional wisdom.
It really does. It's like filling all those glasses quickly somehow.
Well, the architecture of MoE, where only bits of the model activate for specific inputs, that does open up some interesting ways to distribute the work.
Absolutely. And for you listening, if you're trying to get up to speed on these complex topics quickly, get those aha moments.
This is exactly that kind of deep dive.
Yeah, we're going to get into this article. It just came out
All right.
and figure out the secret sauce. How are they seemingly breaking this speed versus volume rule?
Our mission today really is to dissect the core ideas. We need to look at the deployment setups, the architectures,
And crucially, those parallelization techniques they're using.
exactly how they split the work so efficiently. It's straight from the DeepSeek AI team, so it's a good inside look.
All right, let's get into the setup. The article mentions two main ways they deployed this thing.
Yes, they basically compared a single, really powerful machine 8 of NVIDIA's H200 GPUs packed together.
Okay, the heavyweight single node.
Right. And then they looked at using multiple machines, each with 8 H100 GPUs. And they scaled that up to 16 of those machines working together.
So, single big box versus a cluster of slightly less powerful but more numerous boxes.
Pretty much.
But they use a similar strategy underneath for dividing the work in both cases.
That's right. Both setups use data parallelism. You can think of it like having several identical copies of the AI model running simultaneously.
Okay.
And these copies are managed by their own custom request scheduler. It acts like a traffic controller.
Smartly sending requests to the different copies.
Exactly. And it also helps manage something called KV cache reuse.
Ah, the model's short-term memory.
Right. If different requests share similar starting points, the system can reuse that stored info, which saves computation.
Makes sense. Don't recalculate what you already figured out. Now, the article said the model copies, the engine instances, don't span multiple computers.
Correct. Each instance stays within its node. But within that node, they can use tensor parallelism across the GPUs.
Okay, what's tensor parallelism again in this context?
It's basically taking the huge math operations inside the model and slicing them up, so different GPUs within the same computer handle smaller pieces.
Spreading the load locally?
Precisely. And the communication for that inside the node uses NVLink super-fast connections.
Got it.
But when the different computers need to talk to each other, especially for coordinating those MoE experts, that's where InfiniBand comes in. It handles the communication between the nodes for dispatching work and collecting results.
Right. NVLink for internal chats, InfiniBand for cross-machine coordination. And that initial finding about the single H200 machine, fast at first, but then it struggled.
Yeah, that was interesting. With really small batch sizes, just a few requests, it was super quick, very low latency.
Okay.
But as they ramped up the workload, fed it more requests simultaneously, the performance, the speed, dropped off quite a bit.
Ah, there's that trade-off again. So how does the multi-node approach avoid this? This gets us into the parallelization strategies. TP, EP, and DP. Let's start with TP, tensor parallelism.
Okay, so TP, for these big language models, is mainly about cutting down the memory needed on each GPU and also reducing the computation each one has to do.
Right.
You take the big matrices, the linear projections, the attention calculations, and you shard them, split them across multiple GPUs.
You like dividing a massive spreadsheet so everyone gets a manageable chunk. Saves memory, spreads the math.
Exactly. Now, ideally, this means calculations aren't duplicated, but DeepSeek V3R1 uses multi-latent attention, MLA, which adds a wrinkle.
Okay, a complication. What's different about MLA?
With MLA, there's this initial step where it creates a shared latent vector. Think of it like a summary of the input.
A shared summary.
Yeah, and this single summary is then used by all the different attention heads in that layer. because it's shared.
I see the problem. If it's shared, you can't really chop it up easily for tensor parallelism, can you? Each GPU in the TP group needs it.
Precisely. So all the GPUs in that TP group end up needing the parameters and doing the computation to create that initial summary. And since that summary is also stored in the KV cache, that short-term memory, each GPU in the TP group holds an identical copy of that part of the cache too.
So some duplication of effort and memory happens with TP because of MLA. Doesn't sound perfectly efficient.
It's not perfect sharding in that specific part, no. But the article emphasizes that TP still helps reduce the overall computation time.
Okay.
It distributes enough of the other parts of the calculation that it's still beneficial for speed, even with that MLA duplication.
All right, so TP is useful, but with a caveat for MLA. Now, expert parallelism, EP. This seems like the core idea for handling the mixture of experts layers. Remind us what a MOE layer does.
So in DeepSeek v3.r1, and MOE layer has a whole bunch of specialized subnetworks. They call them routed experts, 256 of them.
Wow, okay.
And there's also one generalist shared expert. When a piece in text, a token, comes in, the system routes it to the best 8 out of those 256 routed experts.
The specialists.
Right. It gets processed by those 8, and the results are combined. Plus, every token also goes through that one shared expert.
Got it. Specialist plus a generalist for every token. How does EP spread that workload?
With EP, you distribute those 256 routed experts across your GPUs. So if you have, say, EP8, it means those 256 experts are divided among 8 GPUs. Each GPU handles 32 experts.
Okay.
Crucially, though, every GPU still keeps a full copy of that single shared expert.
Okay.
The big win here compared to just TP is that EP lets you spread the expert computation across potentially many more GPUs. This drastically cuts the work and memory needed on any single GPU.
That makes a ton of sense. Each GPU specializes in a smaller set of experts, but getting the right data to the right expert on the right GPU sounds like a communication challenge.
You nailed it. That's the tricky part. Before the experts can work, there's this all-tall communication step.
Well, tall.
Yeah. Every GPU looks at the tokens it has and figures out which ones need to go to experts living on other GPUs. It sends out, that's the dispatch.
Okay.
Then, after the experts do their math, there's another all-tall, the combine phase, to gather the results back from all those distributed experts.
That sounds like it could really slow things down if it's not efficient. They mentioned optimized kernels using NVSEM.
They did. They knew this communication could be a bottleneck, so they developed highly optimized dispatch and combined kernels using NVSHMEM.
What's NVSH?
It's a tool that lets GPUs share memory really fast. Great for this kind of communication, especially within a node, but also helps across nodes. They even pointed to a previous article where they detailed these optimizations.
Good stuff. Okay, so TP slices layers, EP distributes the experts. What about the third one? Data parallelism, DP. How does it fit in?
Well, EP is great for spreading out the MOE computation, maybe across 128 GPUs or more. But remember, the MLA layers don't divide up so well with EP.
Right, the shared summary issue.
So data parallelism comes in for that. With DP, you essentially create multiple independent groups of GPUs. Each group has the full MLA processing capability.
Okay.
But each DP group works on a different set of input data, different requests. They handle the MLA part independently for their assigned batch.
So it's like multiple assembly lines, each handling different orders, but fully equipped for that tricky MLA step. And these three, TP, EP, DP, they combine.
Absolutely, in a hierarchy. They use the formula EP equal DP TP.
Okay, give me the example again.
On 16 machines, they might use EP128, DP32, TP4. So the experts are spread across 128 GPUs total, that's the EP.
Right.
Those 128 GPUs are organized into 32 independent data parallel groups, the DP.
Okay.
And within each of those 32 groups, the MLA work is split across 4 GPUs using tensor parallelism, the TP.
Wow, okay, that's intricate. Lots of moving parts. Now back to the core question. How does this multi-node setup give both speed and volume? Let's compare the single H200 node versus the multi-node H100 cluster.
Right. First off, the DeepSeek model is massive, 671 billion parameters. It needs multiple devices.
You can't run it on just one GPU.
No way. They did mention that a single 8-GPU H200 node can just fit the model using an DP8 TP1 setup.
Yeah.
Uses about 100 gigabits per GPU, leaving some room for the KV cache.
So it fits, barely. But how does it perform compared to spreading it out more?
That's where the experiments come in, comparing that single H200 node against clusters of H100s, up to 16 nodes, different TP settings, different batch sizes per GPU.
Assuming a fixed KV cache size and predicting one extra token at a time, right?
Correct. And the key finding, shown in those Pareto frontier graphs in the article,
Yeah.
is that higher EP values used in the multi-node setups consistently led to simultaneous improvements in both throughput and output speed, or latency.
That's the counterintuitive win. So what was holding back the single node underload?
In that EP8 setup on the single node, it was super fast with very low load, like batch size 1, tiny bit of work done quickly.
Makes sense.
But increase the batch size, give it more work, and the output speed drops significantly. The explanation comes down to memory bandwidth.
Ah, how fast you can get data on and off the GPU memory.
Exactly. As the batch size grows, more of those 256 experts get activated across all the tokens, which means each GPU in that EP8 setup has to fix the parameters and do the calculations for potentially many more experts. This puts huge pressure on the memory bandwidth.
And that becomes the bottleneck, not the raw compute power.
Precisely. The text generation part is often memory bandwidth bound, so the single node chokes on memory access as the load increases.
Got it. Too many experts trying to grab stuff from memory on too few GPUs. How does the multi-node high EP setup like EP128 fix this?
With EP128, each GPU is only responsible for a tiny fraction of the experts, just in this case, 256 experts, 128 GPUs.
Way fewer experts per GPU.
Right, so the memory bandwidth pressure on each individual GPU is much, much lower. They aren't juggling data for dozens of experts.
Okay.
As a result, when you increase the batch size with EP128, the output speed doesn't plummet nearly as much. They saw something like 5x higher throughput at the same output speed compared to the single node.
Wow, 5x. That's huge. But didn't the article mention a tiny exception where the single node was sometimes slightly better?
Yes, at very, very large batch sizes, the single node could eke out slightly higher throughput. They think it's partly because the internal NVLink connections are faster than the internode InfiniBand.
The internal highway is faster.
Kind of. But they also noted implementation limits might be a factor. And crucially, the multi-node setup is still better if you want to push for really high throughput because it just has way more total memory capacity. The single node would run out of memory sooner.
Right. So multi-node wins for scalability and most practical scenarios, aiming for both speed and volume. No, they also talked about overlapping computation and communication in the MOE layers. Why bother with that?
Well, as we said, EP involves that all-told communication, dispatch, and combine. While GPUs are waiting to send or receive data, they can be idle.
Wasted time.
Exactly. So the goal is to find useful work for the GPUs to do during those communication phases to hide the latency.
Makes sense. Keep the expensive hardware busy. What were the two main ways they did this?
First was dispatch overlap. Pretty simple idea. Remember the shared expert. Every GPU has a copy, and its computation doesn't need cross-GPU communication.
Right.
So after a GPU sends out its tokens for the routed experts, dispatch send, while it's waiting for results back, dispatch recce, it can just compute the shared expert part.
Nice. Use the waiting time productively. What was the other more complex technique?
Microbatching. The idea here is to take a big batch of requests and split it into smaller microbatches.
Okay.
They divide the work in a transformer layer into stages. For the many MOE layers in the middle, they split the batch into 2 microbatches. These run slightly out of sync.
How does that help overlap?
While microbatch 1 is doing its communication step, say, the dispatch, microbatch 2 can be doing its local computations. Then they swap. Since they don't depend on each other within that layer step, one can compute while the other communicates.
Clever. Alternating compute and communication between the 2 mini batches. Did it work well? They showed a latency breakdown, right?
They did. Compared newerlap, dispatch overlap, and microbatch. Dispatch overlap was a bit faster than doing nothing, but microbatch gave a huge 29% speed up in their test case.
29%? Just from smarter scheduling.
Yeah, mainly by drastically reducing the effective time spent waiting on dispatch and combine.
Impressive. But there was a catch with microbatching. It wasn't always better.
Correct. Splitting the batch into smaller pieces actually made the core computation kernels slightly less efficient. They took a bit longer to run on the smaller chunks of data.
Ah, so it's a trade-off. You reduce communication waiting time, but slightly increase compute time.
Exactly. And that trade-off only paid off above a certain batch size. Below batch size 32 in their tests, microbatching was actually slower than just dispatch overlap.
Interesting. So it depends on the workload. What about comparing EP8 single node style and EP128 multi-node using microbatch?
And they found EP8 with microbatch was slightly faster overall in that specific test.
Really?
Well, the group GMM part, the main MOE expert computation, was twice as fast in EP128, as expected. because the work was spread out more. That's the big win for high DP.
Yeah.
But the communication time, dispatch and combine, was longer for EP128. They noted their all toll wasn't fully utilizing the InfiniBand bandwidth, maybe only using half. So there's room for improvement there.
Okay.
Also, the regular matrix multiplications, GEM, were slower with microbatching in both cases, not just the group GM.
So distributing the experts helps the core MOE math a lot, but the communication cost currently eats into that benefit somewhat, and microbatching can hurt raw calculation speed.
Yeah.
They used the roofline model to analyze this.
Yeah, the roofline model helps visualize if a computation is limited by the processor's math speed or by how fast it can access memory. It looks at arithmetic intensity, FLOPs, per byte of memory I/O.
Okay, helps find the bottleneck. What did it show for the MOE computations, the group GM?
It showed group GM is largely memory bandwidth limited. Its performance depends on the total number of tokens being processed by the experts. Increasing the number of tokens per expert generally improves performance because it increases that arithmetic intensity, making better use of the memory bandwidth.
So feeding the experts bigger chunks is better, up to a point. What about the regular GMM, the linear projections?
Also, memory bandwidth limited, typically. Performance improves as the batch size increases, again, because that boosts arithmetic intensity.
Right. Which explains why micromatching, by effectively reducing the batch size for those kernels, can hurt their efficiency.
Exactly. It lowers the arithmetic intensity for those steps.
And multi-token prediction, MTP, helps how?
MTP, predicting more than one token at a time, effectively increases the amount of computation done relative to the input size. For GM and group GM, it's like processing more tokens per expert, or a larger effective batch size.
Ah, so it boosts that arithmetic intensity again.
Yes, making those memory bandwidth limited kernels run more efficiently. It also significantly helps the MLA kernel efficiency according to their roofline analysis. So MTP is generally a good thing for performance.
Okay, this is deep. They also quickly mentioned implementation details, like using FP8 for numbers.
Right, native FP8 training, they use per block quantization. So static weights are quantized, but activations are quantized on the fly with scaling factors calculated over smaller blocks, not the whole tensor. Helps accuracy.
And using both CDA and Triton for coding.
Yeah, CEDA for the really speed-sensitive stuff like attention and matrix multiplies where they need absolute peak performance. Triton gives them more flexibility for things like custom activation functions, normalization, and implementing that block quantization easily.
A mix and match approach.
Definitely. They even mix different GEM kernels, their own deep GM and custom Triton ones, depending on matrix shapes and batch sizes, to squeeze out performance.
And they had some challenges making dynamic things work with CDA graphs, like routing tokens to experts.
Yeah, block quantization needed tweaks to work in CUD graphs. And the MOE router is tricky because the number of tokens going to each expert isn't fixed beforehand. They use a special approach where GPU blocks continuously poll for work and dynamically divide it up.
Clever workarounds. And they built their own all-toll to handle varying batch sizes across DP groups.
Exactly. The standard torch.alto single needed all GPUs to have the same tensor shape, which wasn't always true with DP. Their custom kernel removed that limitation, making communication more efficient when batch sizes were uneven.
It's just layer upon layer of optimization. And sounds like they're not done yet. Future work.
Big one is prefill disaggregation. The initial processing of the prompt prefill is computationally different from generating the response token by token, decode.
Right.
They think these phases might need different optimization strategies, maybe even different EPDP configurations. Converting MLA to standard attention for prefill could be faster, but the way the KV cache stores latent vectors makes it hard currently.
So potentially treating prefill and decode differently. What else?
Improving that all-toll performance, get closer to the actual InfiniBand speed. Implementing speculative decoding, like EGLE, to predict multiple tokens ahead. Optimizing the GMM kernels further. And exploring NVIDIA's next-gen hardware like the GB200 NVL72, which looks really promising for MOE.
Always chasing more speed. Okay, let's wrap this deep dive. What's the big picture takeaway here?
I think the main thing is that, yeah, with MOE models like DeepSeek V3R1, you can break that old trade-off. Multi-node deployment, when done right, really can deliver both lower latency and higher throughput simultaneously.
And the key is distributing those experts widely using EP.
Exactly. That alleviates the memory bandwidth bottleneck on individual GPUs, which unlocks both speed and scale.
But it requires careful orchestration using TP, EP, DP, and these overlap techniques like microbatching, all while managing the trade-offs they introduce.
Absolutely. It's complex, and the optimization is clearly ongoing, looking at everything from kernels to communication to hardware.
So for you, the listener, hopefully this gives you a solid grasp of how these advanced deployment strategies work. Understanding this stuff is crucial as MOE becomes more central to building the next wave of powerful AI.
It really is. Which leads to a final thought to chew on. Given how fast both the models and the hardware are evolving, what other performance barriers, things we currently accept as limitations in AI, might crumble next thanks to clever deployment and optimization? Definitely something to ponder, and maybe even check out that DeepSeek technical report for more details.